So we're going to do a lesson today on sketching graphs of polynomial functions. So we're basically putting all of the ideas we learned together onto here's a formula, what does the graph look like, including the x-intercepts now. So you have to remember that the degree tells us kind of the basic shape, okay? We kind of talked about whether the graph is going to have kind of an up-up pattern, a down-down pattern. This is sort of even degrees. So they're either going to be both up or they're going to be both down. And then a funky smile in between or a funky frown in between. I know that odd degrees are going to have an up-down pattern or a down-up pattern. So what we mean by that is either one arrow is up in quadrant, this would be quadrant 2 to quadrant 4 behavior, or this one would be quadrant 3 to quadrant 1 behavior. This one would be quadrant 2 to quadrant 1 behavior, quadrant 3 to quadrant 4 behavior. So if I look at my graph, remember this is 1, 2, 3, and 4. So the leading coefficient will also kind of give us the end behavior of the graph. So when you kind of think of a parabola, you think of a smile being positive, a frown being negative, so forth. So basically, like on an even degree where the arrows are both pointing down, my leading coefficient would be negative. And then when my arrows are both pointing up, my leading coefficient is positive. So you want to think like a quadratic under this column. And then under this column, you want to kind of think like a linear, because the linear is going to kind of give you the behavior of all of the odd degree functions. So quadrant 3 to quadrant 1 would be kind of like a positive slope. So this is my positive leading coefficient. And then quadrant 2 to quadrant 4 behavior would be a negative leading coefficient. So hopefully you have those rules kind of somewhat in your head. But if you don't, again, think of the positive quadratic, the negative quadratic, the positive linear, the negative linear. That will help you with all of those behaviors. The constant term tells us the y-intercept. So this term will have no variable attached to it. And factors tell us the x-intercept. So now, when we want to factor, we're going to use the ideas we just learned last week, which is the remainder theorem. Remember, we have 3 steps for the remainder theorem. Step 1 is to define p of x. Step 2 is to look at x minus a, and then find the x equals a. And then step 3 would be to sub in that a value into my polynomial, and the answer would represent the remainder. Okay, now we want to add on an idea here that we didn't have before. The possible integral zeros would be the factors of the constant term. So those are the things we want to try for step 2, because they may not give us the x minus a term. They may make you figure that out. Okay. Multiplicity will kind of tell you how many times the graph crosses the x-axis and how it actually crosses. So how many times it crosses and the shape at which it crosses. Or I'll call it the shape at the x-intercept. So for example, if I have an x-intercept that has a multiplicity is 1, that means that my graph would just kind of go through the x-axis at that x-intercept, which I'm just going to call x-intercept. If my graph has a multiplicity of 2, which means I have perhaps an x minus 2 times an x minus 2 in a bracket and potentially other stuff, it means my graph is going to kind of touch the axes and then bounce off at that x-intercept. Okay, and I'll show you what we mean by this a little more detail as we get to the examples. And then if my graph has a multiplicity of 3, which means you get a factor that's repeated 3 times, like a bracket with x minus 2 written 3 times out, we call that kind of like it goes through the axes, but it kind of does it in a slide format. So it's kind of sliding through the x-axis. So I call this a slide. This one is called a touch. And this one is called a cross. Now these are names that I just make up. They're not actual formal names that we use. So again, when they ask you for the multiplicity, you can think of cross, touch, and slide. But again, multiplicity is the specific number of times that you see a factor occurring. Okay. So now let's just look at the next example, and it says analyze the following functions by stating the degree. So we know how to do this. We've already done this. This should not be new to you. So to find the degree of the function, we sort of count the number of terms. That's 1, that's 2, that's 3. So my minimum possible degree is going to be 3 in this example. Now I'm going to get rid of those lines so that I'm able to do other stuff on there. Now the sign of my leading coefficient, if I were to take this piece and this piece, which are facing in opposite directions, and connect them with a line, is this line have a positive or negative slope? When I look at this, I'd be like having fun, kind of sliding down that hill. So this would be a negative leading coefficient. So you're just thinking of it as like a linear, but it's not a linear. I'm going to delete that out of my spot there. What are the x-intercepts? And let's even write the multiplicities here. Okay, so this is an x-intercept. So I'm going to write the x-intercept, which is -2 and 0. And then it sort of does the behavior like this one, which is a touch. So I'm going to kind of write that it's a touch, which means the multiplicity would equal 2. So the x equals 2 would be my root, but the x plus 2 would be my factor, and that factor would occur 2 times. So I would have 2 brackets of that. This x-intercept is at 3 and 0. It kind of does a cross through the axes. So you can kind of think of it as a cross. And then that means my multiplicity is 1, but I would see that bracketed term, x minus 3, 1 time. So that would be the factor, but it would occur 2 times. So if I put these two together, that's likely going to be my polynomial, but there also has to be a negative leading coefficient. But you never know. There might be a number that's out front here that's affecting the slope or the wideness or narrowness of the graph. What are my factors? Well, for sure, I'm going to have an x plus 2 squared factor. And then for sure, I'm going to have an x minus 3 factor. Otherwise, I'm not going to get a cubic polynomial. I'm not going to get a degree 3. So I need 2 of these brackets because that's sort of doing a touch. And then this one is doing a cross. So we know that it has to have that factor 1 time. Intervals where the function is positive or negative. Sometimes this tends to trick people. But what we want to do is look at the y values here. Keep going, look at the y values all the way till I get to that point. My y values are always positive with the exception of being 0 here and here. So it's almost like I want to make a number line. And on this number line, I want to represent my x-intercepts. And I want to kind of base base the value of the function between the x-intercepts. So this branch of my function is between negative infinity and minus 2, and that branch of the function is positive. This branch of the function is between minus 2 and 3, and that branch of the function is also positive. And then this branch of the function is after 3, so that would be negative because it's sitting below the x-axis. So my function, function f of x is positive on the interval minus infinity to minus 2, open bracket, because at 2 it's equal to 0, and then union negative 2 to 3. because at x equals 2, it's not even positive or negative, it's just 0. F of x is negative on the interval 3 to infinity. And again, I don't want to include 3 in my point because 3 is not really a function being positive or negative. At x equals 3, I'm exactly 0. Okay. Let's look at the next example. Analyze the degree. So let's count. 1, 2, 3, 4. So it looks like a 4. I know that both ends are pointing down, so that also tells me that I'm kind of in a even degree function. My ends are both pointing down, so if I was kind of comparing this to a quadratic, I would have had a negative leading coefficient. I want to look at my x-intercepts, so -5 and 0, -1 and 0, and 4 and 0. This is doing a cross, and a touch. So this multiplicity is 1, multiplicity is 1, multiplicity is 2. So that's going to help me determine my factors. If my x coordinate is 5, then my factor is x minus 5, and it has a multiplicity of 1, so I'm going to put an exponent of 1. My factor here is x equals -1, so the bracketed term, or sorry, my root is x equals -1, so the factor is x plus 1, and it has a multiplicity of 1. And then here, my root, or my x-intercept, is 4, so the factor would be x minus 4 squared. So that would be my factors, or put together, like I put this together and I get a polynomial, but basically I know here there has to be a negative leading coefficient, and then potentially a number that will determine whether my graph is skinnier or wider than the normal quartic graph of this sort. Now I'm going to draw a number line to separate my graph. The lowest x-intercept is -5, then -1, then +4. So my graph is broken up into 4 sections. So in the first section, my graph is negative. Ooh, that's a little bit hard to read. I'm going to use a different color. So in this section, my graph is negative because it's below the x-axis. In this section, all my y values are positive. In this section, all my y values are below, so negative. And then in this section, all my y values are negative. So now to write a summary of what we just said, f of x is positive on -5 to -1. We will never include the endpoints because at the endpoints are the x-intercepts, and at the x-intercepts, my y is exactly 0, not positive or negative. My function is negative on -infinity to -5, union -5 to -1, union, whoops, not -5 to -1, messed that up, -1 to +4, and then +4 to infinity. Okay, so this is just literally taking everything we done in the early part of the unit, and the only new aspects are the x-intercepts and the multiplicity, and then we never asked this to you before, but we are asking it to you now. So this is analyzing a graph of a function that's already given to you. Now it says to sketch the graph. So I give you a formula and you need to sketch it, and it says do as much by hand as possible. So I know my type is going to be x, x, x. Multiply all those x's together. I get x to the power of 3, which is a cubic function, which means I know my degree is 3. Now, in terms of figuring out your leading coefficient, I need a smaller marker. We look at this x right here. That's a +1, a +1, and a positive. So 3 positives make a positive. So I know my leading coefficient is positive because those 3 multiplied would give me a positive result. what is my x-intercepts with their multiplicity? So one of my x-intercepts is 1 and 0 coming from that bracket. One of my x-intercepts is -2 and 0 coming from that bracket. And then my other x-intercept is -3 and 0 coming from that bracket. All of them have an exponent of 1, which means when I draw the graph, my multiplicity is 1. And when I have a multiplicity of 1, I want to think of a cross for each one of these. So my graph is just strictly going to cross. Because I have a positive leading coefficient, I need to think of a positive slope graph, which is why this is in quotations. So it's going to have quadrant 3 to quadrant 1 behavior. And then the only other piece of information I really need is my y-intercept. So in this case, I sub in x is 0, 0 plus 2, your traditional way of finding the y-intercept. -1 times 2 times 3 is 0, -6. So let's plot that. 1, 2, 3, 4, 5, 6. 1 and 0, -2 and 0, -3 and 0. And then I'm just going to draw it. Now remember those little bumpies on a cubic? The high point of this or the low point of this, we don't actually know where they are without a calculator. So I'm going to sketch this as much as I can without the calculator. But the location of this point and this point, I don't know where they're going to end up. I don't know if it's going to be on the y-axis or shifted over. I probably should even be a little bit careful because when I'm drawing this graph, I shouldn't necessarily make my y-intercept the bump. The bump does not have to be at the y-intercept. The bump could be at that point. Whoops, I deleted it again. Let me just draw that in again. So up, down, goes through 1, 2, 3, 4, 5, 6. Goes back up. Oh, and I did it again. I'm going to make it go down lower and then go back up. So again, I don't know the location of these bumps without the calculator. Okay, so that would be a good sketch without the calculator. And then if I was looking for accuracy, then you have to do the calculator. So I'm just going to call this an approximate graph because I don't know where the bumps are going to be until I calculate that point and calculate that point. But again, on a test, if I ask you to sketch the function, you would want to do the graph properly. So you can use Desmos, find out where that or where those bumps are going to be, and then sketch it like that. Now on this graph, we're going to use a scale of 10 units. So each point on the graph is going to be 10 units for the y-axis. So let's try to start by figuring out what the characteristics of my graph are. So let's start with the type. So this graph, and I'm going to try to make it bigger, there's a positive x, a positive x. So this is x cubed times x times a negative. So x cubed times x is x to the 4th. So I have a quartic function happening. My degree is going to be 4. My x-intercepts, or even before I get to that, it has a negative leading coefficient for a power 4. So you're kind of thinking of your negative quadratic. It's a smile with some funky turns in it. My negative leading coefficient would mean I have quadrant 3 to quadrant 4 behavior. So I know my ends are going to both point down, and there's going to have some funkiness in the middle. My x-intercepts are -2 and 0, and because this exponent is a 3, my multiplicity is 3. For that bracket, my x-intercept is 4, 0, and my multiplicity for that bracket would be 1. So when I draw this graph, this is going to kind of do a slide. It's either going to slide this way or slide this way, depending on how we need the graph to be. And this one is going to do a cross at 4. So 1, 2, 3, 4, there's an x-intercept. 1, 2, there's an x-intercept. Let's calculate my y-intercept. So sub in x is 0. So when I sub in x is 0, I'm going to just work that out. So 2 cubed is 8. 8 times minus 4 is minus 32, and then another negative sign on the outside, which makes it positive 32. So remember, they're telling my scale is 10. So 10, 20, 30, so negative 32 is down here somewhere. Again, we're not going to know where the little bumpies are because the bumpies could be anywhere. Like I could have a funky curve like this. These bumpies, we won't be able to know where they are unless we use Desmos or our calculator. Now, I'm not going to focus on that too much, but I will show you on Desmos how you find those. So basically, we have all the points we need. I'm going to kind of draw a rough sketch and then modify it after I get the values of those bumpies. So it has to do a slide at -2, but my graph has to be facing down over here. So I'm going to start my graph by going down. It has to do a slide. And then it's going to go across at 4. So it's going to go up, probably back through, and then, ooh, something went funny here. Let's look at the graph on Desmos because I'm in the middle of a recording and I don't want to stop. Okay, so we're going to sketch in minus bracket x plus 2 to the power of 3 times x minus 4, x minus 4. So that's why I plotted my y-intercept wrong. You can see it's on the positive end, but I could figure out something was quite wrong when I was drawing it. So there's my y-intercept, which is my mistake. Now the value of these bumpies, we might as well get them when we're here. It's 2.5 and approximately 137. So I'm just going to go write that back down. 2.5 and 137. 2.5 and 137 is a bump. I'm going to automatically erase this because I plotted my y-intercept wrong, which is why I'm having trouble figuring it out here. When I go back to my graph, I need to find some more bumpies because the end behavior of my graph is facing down. So it's going to do a slide. It's going to go up. It's going to hit this maximum of 137, and then it's just going to come all the way back down, do a cross through 4, and then face back down. So when I draw this, let me actually plot my y-intercept properly this time. So 10, 20, 32, 10, 20, 32, which is somewhere there. And then at 2.5 and 137, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 10, 20, 30, 40, if I've counted that right. Maybe somewhere there, and now my graph can make more sense. So it does a cross, it has to go up, across through that point, and then come back down without my shaky hand in there. Okay, so down, slide, up, cross, down. Okay, now we want to make sure because this is a sketch, I want to label my graph. Again, we haven't been doing a great job of labeling things, so let's label this. We want to label my x-intercept, that's a key point. Label my other x-intercept, that's a key point. Label my y-intercept, that's a key point. And then that point is also key, but I'm going to highlight it, and I'm going to put approximately 137. This point is not able to be done without using a calculator. So this one has to be done on the calculator. And that's why they're saying to sketch as much as possible by hand, but you can't do everything. So again, I never actually made this graph accurate because of, I didn't make this graph accurate because I didn't find those little bumpies on my calculator. Now, in terms of this last question, these are some really good problems, example 3, because what they expect you to do is kind of take the characteristics they already give you and then make you sketch the graph. So let's start by using the characteristics we know. We have a y-intercept at 0, 9, so let's go ahead and plot that. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm going to plot my graph in red. Okay, make sure you're plotting it at the right point. So I'm going to put a check mark here. I have a 0, and another word for 0 is x-intercept. Okay, so when x is minus 1, I have an x-intercept, and when x is 3, I have an x-intercept. So I put my x-intercepts there. The 0 at x equals 1 has multiplicity 1, which means it's just crossing at this point. And then the 0 at 3 will have a multiplicity at 2, which means it has to touch. Now, we don't know whether the graph is going to face up or down. So what I'm going to do is I'm going to make this graph cross at 1. So I'm going to start from quadrant 2. I'm going to make it come down, make it cross at -1, make it go through my y-intercept, come up. I made a little bumpy here, which I don't know where it's going to be. I'm just going to estimate it. It's going to do a touch at this x-intercept and then bounce back down. And then I have to stop because there's no other x-intercept. So if I take this multiplicity and add it to this multiplicity, I get a total of 3, which is probably leading me to my degree of 3, which makes sense for this diagram. I just made it have a quadrant 2 to quadrant 4 behavior, which means I have a negative leading coefficient. So please make sure you work through the questions at the back of the lesson and the multiple choice section and see if you can problem solve your way through some of these ideas now that we have most of the unit there. Now I could give you this polynomial, for example, and instead of giving it to you in factored form, if I gave it to you in standard form, now you're going to have to use your remainder theorem, your factor theorem, and all that jazz to be able to factor it before you do all of this graphical stuff. So basically, when we go back up here to the factor theorem, remainder theorem, once we do step 3, we can get to factor theorem, which is step 4, which would be if remainder equals 0, then x minus a is a factor. So all of that material we learned late last week will be applicable if they give me the polynomial in standard form, so not in factored form. Okay, this is all the stuff from last week. This is the new material we did with the synthetic division. So this is also the synthetic division stuff. So hopefully that made sense, and if you have any questions, feel free to email me.